All right, today's the 5th, October 5th, probability, introduction to discrete random variables. So we are finally at the main part of the course. Introduction to discrete, and we'll do continuous random variables. One of my professors once remarked years ago that it's a shame that any book has to be totally ordered along the page axis, is you have to choose an order to do things. If you are looking at probability, a lot of the things for discrete random variables and continuous random variables are fundamentally the same. What differs is a little bit of the algebraic techniques you use to attack some of these things. But the fundamental ideas, the fundamental techniques, the fundamental definitions are almost entirely the same. In terms of actually presenting something in class, you typically have to choose something. So a lot of books and a lot of courses first do a whole spiel on discrete random variables, and then they go through and then they do a search and replace, and they replace the words discrete with continuous, and for the most part everything follows similarly. I'm going to try to do the two simultaneously to free up more time to do interesting applications later in the semester. Okay, what do you think the fundamental difference is between discrete and continuous? I can hear a pin drop. Yes?
Continuous take all values.
So continuous will take all values, discrete will take a subset of values. Typically the subset will either be finite or it'll be a countable infinity, say 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, 5, or maybe dot, 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 negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. Those will be the types of discrete processes we will study. What tool do you think would be useful for calculating probabilities for continuous random variables? Calculus. In particular, which part of calculus? The name. What's the name of the big result in calculus? The fundamental theorem of calculus. There are not that many fundamental theorems you have learned. How many of you know the fundamental theorem of linear algebra? Good, I always thought that title was pretentious. I do not think that result merits fundamental status. The fundamental theorem of calculus, this is important. Areas under curves can be given by antiderivatives. Unfortunately, what does this require in order to be useful? You have to be able to find antiderivatives. Most of the time, you cannot find antiderivatives of functions. You can numerically expand, you can numerically approximate, you can simulate, or you can cherry pick which distributions you are looking at because they happen to have nice antiderivatives. And that's what we will frequently do, and we'll just cross our fingers and say that for the most part, they actually do a decent job of modeling a lot of natural phenomena. And sometimes, in fact, they are exactly what's going on. The other thing, in terms of all the stuff that's going on, is apples versus oranges. Hopefully you've heard this expression sometime in your life. You don't want to compare apples and oranges. You want to compare two things that are the same. Which is it better to have, $100 or $200? I'm very hard pressed to come up with a situation where having more money is bad. Maybe in an extreme case you have so much money people will now try to hurt you to get your money. For the most part, we all agree it's very easy to compare. If I have a choice between two amounts, I want the greater amount. When you're buying a house, when you're buying a car, you are not comparing apples and apples. This house has a better location. This house has more space. This house has a better school district. Which one do you want? Similarly, looking at cars, they have different features. It's very hard to compare. When I toss a coin, what are the possible outcomes? Heads and tails. This is what you've been trained to say. Think of it another way. We've seen over the programming aspects of this course that it's often much better not to use the natural labels that society is fostering upon us. We've changed the Sudoku. What should we do for coins? The outcomes are either 1 and 0 or... No. We don't want heads and not heads. Nope.
10 and 1.
No. It's either, you said 1 and 0. So toss a coin, 0 or 1, or the other possibility is or 1. What should the other one be? Negative 1. The advantage of this is now balanced. If I want to sum the outcomes, if I have the same number of heads and tails, the sum will be 0. If I look at this one, the advantage is if I sum the number of outcomes, I get the number of heads. So they both have advantages. Advantage, sum of tosses is the number of heads. The advantage, sum of tosses is 0 if balanced. You always want to think about how do you want to express something, how do you want to define something. So we say a random variable is a map from elements of an outcome space to the real numbers. So basically x maps omega to r. And we'll often denote this by using really big notation. X of omega will be our specific value. In a lot of books, they use boldface for random variables. Why do you think I'm using capital letters with lines on them? What do you mean I can't? Excuse me. I can bold. Thank you. We don't have much time. For me to be spending this much time is problematic. So it's much faster for me to go boom, boom. So you always want to think, what notation are people using? People are using this notation. I actually have a colleague who does not like using certain notation in writings because that's the notation we're using in blackboards, and we're only using that notation in blackboards because we can't do things in writing. So just think, how do we want to do it? I'm going to do things like this on the board to make it easy. Sometimes books use arrows over vectors to just really drive home the fact that this is a vector. Notation is supposed to be useful so you can glance down and see what's going on. So what we want to do is we want to look at different places. Oh, good, it's actually tracking today. We want to look at different places where we can define random variables. So let's toss 3 independent fair coins. So let's let x1, or let's xi equal 1 if a head on toss I, and we'll do 0 if a tail on toss I. So this is probably one of the easiest random variables to understand. Okay? Just basically, it's an indicator function. It happens or it doesn't. In fact, it's a binary indicator function because there's only 2 possibilities. You get a head, you don't get a head. Given random variables, we can create new random variables from these. We could let x be x1 plus x2 plus x3. This is a new random variable. You have to sometimes be a little bit careful as to what is your outcome space. Is xi, what does xi take as input? What's my input here? I'm sorry? A toss? That's my output. My output is a real number. What's my input? Nope. Nope. I toss 3 independent fair coins. My input here is a triple of outcomes, heads and tails. So the input for xi is a triple of heads and tails. Right? I'm tossing a fair coin 3 times. And then xi will tell you. So for instance, if I look at xi of head, tail, tail, what would I get? 1. This is often overkill in notation. And people get lazy and they start suppressing things. The more comfortable you are with the material, by all means suppress things. It goes back to calculus. If you're integrating in calculus, do you write on the boundary of integration x equals a to b? You often suppress what you're integrating over. It's sometimes useful if you have a lot of things in play to just give yourself little reminders. You want notation to be helpful but not overly cumbersome. What we're really doing here is these x's are defined on triples. Could I define xi on a singleton, on just one toss? Sure. It's a little bit more useful if I want to now add them together to have them all living on the same space. They all take the same event, and now I can add them together. Yes?
Why is not x1 equals 1? We're not
Oh, sorry. This should be, I'm sorry, this should be x2. Sorry. I'm sorry, this should be x1. The toss on the first one is ahead. And if I did x2 of head, tail, tail, that would be a 0. If I define it like this, all the x's and the x, they have the same domain of definition. It makes sense to add them. It makes sense to combine them. Do you think I should be able to understand x from knowing x1, x2, and x3? Yeah. So the question is, and this is one of the fundamental questions in probability, given some simple events, given some simple random variables, can you understand more complicated random variables? So we want to pass from simple to complex. And so one question we could ask is, what is the probability that x equals k? Well, what are the possible values of k that I should be concerned with? Zero, 1, 2, and 3. So it's going to be if k equals 0, if k equals 1, if k equals 2, if k equals 3, and then 0 otherwise. So we're assuming we're tossing 3 fair independent coins. What's the probability we have 3 heads?
1/3.
I'm sorry?
1/2 to the third.
1/2 to the third. And that's the best way of phrasing it. Well, almost the best way of phrasing it. You could phrase it a little bit better than 1/2 to the third.
3 choose 1 over 3 choose, or, sorry.
It's 3 choose something. 3 choose 3. 3 choose 3, 1/2 to the third. For the next one, I want to have no heads. What would no heads be? 3 choose 0, 1/2 to the third. For this one, 3 choose 1, 1/2 to the 1, 1/2 to the 2. And this one would be 3 choose 2, 1/2 squared, 1/2. You can now see why sometimes it's better not to consider a fair coin. When you look at the fair coin, it's a little bit hard to see what's going on. This 1/2 is actually 1/2. I'm sorry, this 1/2 is 1 minus 1/2. If it was probability P of a head, we would get, say, the probability that x equals 2 would be 3 choose 2, p squared, 1 minus p to the first. And what's going on is we have 3 possibilities. We have to choose 2 out of the 3 possibilities to be a head. Once we choose these to be a head, the probability we get a head in each one is p. So we get p times p. And then for the remaining one, it has to be a tail, which happens with probability 1 minus p. So we can use this to figure out the probability that x equals k. What's going to be nice is later on, we might be concerned with certain general properties about this. We might be considered, on average, how many heads do I expect to get? So if I were to toss a fair coin 3 times, how many heads would you expect to get? 1.5. And then you can start to ask questions about, we expect to have 1.5 heads. What do we expect the fluctuations to be about 1.5? We can actually answer these questions extremely well just by knowing things about these simple random variables, these x's. This is one of the fundamental themes of the course, is you want to reduce something complicated to something simple and understand the rules of combining. The rules of combining are often extremely difficult. So let's look at a special case. and just see how bad things can be. So I want to give you two different random variables, and I want to understand their sum. So given x and y, do we know x plus y? So I'm not saying anything else other than I know my first random variable has this distribution. I know my second random variable has this distribution. Do we know anything about their sum? What are some extreme cases we could look at? Give me an extreme choice for y. Well, if y is always 0, it's not going to be too bad. The extreme values for y should somehow be related to x. What would be a good choice for y?
X.
Yeah. Y equals x. So what's the answer in this case? 2x. If y always equals x, then x plus y is just 2x. What's another extreme case?
Y equals 2x.
It's the same in this case, though.
Y equals x complement.
Well, x is a real number. Y equals negative x. Imagine we have a distribution which is symmetric. If a distribution is symmetric, the distribution of x and negative x are the same. In this case, what would be the answer? 0. So unfortunately, if I just tell you I have two random variables, it is hopeless to figure out what's going on. This is why we need the independence assumption. And if we assume x and y are independent, then there are great ways of combining the distributions of x and y to get the distribution of x plus y. How many of you have played Risk or Monopoly, Backgammon, any of these games where you roll die? Imagine the die are glued together. Okay, if the die are glued together, all of a sudden the sum of the rolls is not so interesting once you know what one of the values is. Okay? Typically, you're not allowed to play like that. So we want to consider cases where x and y are independent and then try to figure out what is true. Now, in the book, I go through calculating, rolling two fair die and looking and seeing what the distribution is. The distribution can be calculated by brute force. It's not too bad. You can do it for rolling 3 die, 4 die by brute force. It's not so bad. As you start getting further and further along, the calculation is doable but less enjoyable. Definitely by the time you get to 8, you no longer want to be doing this. Almost surely you no longer want to be doing it well before 8. Mathematica, I think, gives up around 8, if not earlier, in terms of it no longer wants to spit out the exact formula. For sums of 4 random die, no problem. One of the big themes of this course is the more times you do things, the more things average out. And while we may not know exactly where you are, we can be extremely confident that you are approximately at a given place. For a lot of things, that's good enough. Anybody know what the US current debt is?
13.
It's much more, it's more than 13 trillion. I mean, I know it's over 16 trillion.
26 trillion.
I don't think it's as bad as, how much is it?
Or 17 or 18.
17 or 18. I haven't checked in a while, so it's around 17 or 18 trillion dollars. If I tell you we have this new plan that's going to cut $10 million from the budget, is this significant? Sadly, not really, relative to something of size, 17 trillion. You always want to see how big is the object you're studying relative to the object you care about. And for a lot of practical purposes, we don't need to evaluate these things that well. We're going to have, in some situations, sums of 10,000, 100,000, a million random variables. In terms of knowing how accurate something is, we may be trying to calculate a percentage. Anybody aware that there is a presidential race coming? So there are certain states like New Hampshire that don't have a strong local media market, so people have to buy in nearby states. Vermont is the same way. New Jersey is the same way. I won't be surprised if we get a lot of campaign commercials in the near future. One of the big things people want to know is how strong are certain candidates' support. They're going to do polling, and they're going to try to estimate the true probability of people supporting someone. And we're going to be doing calculations like this all the time. We'll be summing independent random variables. And we want to basically get not the exact answer, but something close to the exact answer with a high degree of confidence. Okay, so let's come back over here to this nice formula. So we call this a PDF, a probability density function. Sometimes people use mass instead of density. To highlight discreteness. You can use distribution. A lot of people use slightly different language, which makes the subject so much fun to read. You can look at lots of different books and they use slightly different language. The most common is a PDF. Sometimes they say PMF, probability mass function, to just highlight so you can glance down and you know it's discrete. This is where words can help. It can just frame your viewing. And so the idea of a probability density function or probability mass function is I specify how likely different outcomes are. How likely is that I get a 0? How likely is that I get a 1, a 2, a 3? We can do all of this for a continuous random variable. How likely is it for a continuous random variable that I get the value 0? Zero. So this is the fundamental difference between continuous random variables and discrete random variables. For a continuous random variable, the probability of a singleton event is 0. In some cases in the real world, you actually have mixed distributions. Distributions that assign a positive probability to certain singletons and then a continuous probability on other things. In this course, we will look at pure cases. Either we have something that's purely discrete or something that's purely continuous, not something that's mixed. It's not so bad to deal with something that's mixed. You break it up into two things. So here we have a couple of discrete options and everything else is 0. In the continuous case, we're going to be given a distribution and then we're going to calculate probabilities by integrating this distribution. Okay. 2 for 2 and having it move. Excellent. So properties of probability density functions. Can anybody give me a really obvious property that a probability density function must have? So the sum or the integral has to be 1. Sum integral must be 1, i.e. something happens. Think of it as you have a probability of 1 that you have to spread among all the different events. It's got to go somewhere. You're not allowed to keep any probability in the bank. If so, that's another outcome. So in the discrete case, it would be the sum of f of xk. K goes from maybe 1 to infinity. In the continuous case, it would be the integral maybe from minus infinity to infinity, f of x dx. Instead of using the letter f, what letter do you think people sometimes use? P. Sometimes people use p, and sometimes you might go, k goes from 1 to infinity of p sub x of xk. And these should both be 1. Minus infinity to infinity of p sub x of x dx. Why do you think I'm putting on the subscript x? Yes? To know which random variable I'm talking about. As you go further and further, you could have several random variables in play at the same time. If you put on a subscript, you can quickly look down and see, oh, okay, I'm talking about this random variable. So even when it's clear, I do like to put on the x here so I can see what I'm talking about. So this is the first property. Something happens. there is another property that we want.
It should be between 0.
So it should be between 0 and 1. Does that mean the function f is always between 0 and 1?
The integral.
The integral. So what we have over here is px of xk is greater than or equal to 0. I don't have to give an upper bound on this because I know the sum is equal to 1. All I have to do is say that this is non-negative. No matter how unlikely an event is, its probability cannot be less than 0. Any baseball fans here? Anybody know what the Rangers did, I think, 2 games ago?
1.
No.
Tied.
They needed to just win that game to clinch the AL West. They had a 4-run lead going into the 9th inning, and they gave up 5 runs. Yeah, there were a lot of websites that were calculating just how improbable it was for the Rangers to blow this big of a lead this late in the game. It was extremely improbable, but there was still some positive probability that it would happen, and it did. There was not a negative probability. So one of the natural conditions is we want px of xk to be greater than or equal to 0. Over here, the corresponding thing is we want our density to be non-negative. Now, if you want, you could put an upper bound here of 1. We can't have the probability of xk being larger than 1. But that comes naturally from this condition here, that the sum has to be 1. It is possible for the density to be greater than 1, but not for long. So this is one of your homework problems, is to show that you can't have the density greater than 1. It's only the integral that has to be 1. So another way of looking at what's going on in the continuous case, so continuous case. So x is a random variable with density p of x. Then the probability that a is less than or equal to x is less than or equal to b is just the integral from a to b of the density dx. And if you want to plot it, here's a, here's b, and we just take the area under the curve from a to b. So that would give us the probability that our random variable takes on a value between a and b. And if you take a and b to be equal, what's the probability? A less than or equal to x, less than or equal to a. This is the continuous case. What would that equal? 0. So in the continuous case, we are assigning probability 0. This has caused a lot of issues over the years in probability classes. Let's say I'm uniformly choosing a number from 0 to 1. So all numbers are equally likely to be chosen. I choose a number. What was the probability I chose that number? But I chose it. How could I do something that I can't do? So there's lots of different explanations. One of the explanations is, fine, you chose the number, but you'll never choose it again. If we're doing anything in the real world, can I choose anything from the continuum? Can I choose any number from 0 to 1? Now, you might have doubted my ability to do blowed x's. I think I demonstrated I do have that power. I do not have the power to choose an arbitrary real number. What's the best I can do? I can choose some kind of computable number. Maybe I have a decimal expansion or a finite binary expansion. I go certain amounts of times. Computer only does finitely many operations. And I can choose something like that. For all practical purposes, it's continuous. For all practical purposes, it looks like I can choose any number. But I'm not. I'm really looking at something discrete. Why would I model this with something that's continuous? Because I now have the tools of calculus at our disposal. So we'll have a lecture later in the semester on baseball mathematics. And we'll talk about some of the issues between discrete and continuous, how you can use mathematical modeling to solve a variety of very interesting real-world problems. Okay, any questions? Yes?
So I guess I'm still confused about the continuous side of the second property.
Oh,
So
okay.
can P of X ever be greater than 1 at any, like, instantaneous, like, any
Yes,
point?
absolutely. In the continuous case. It just can never, we know that the integral has to be 1. It can be greater than 1 on a very small subinterval. So it could be greater than 2 on an interval of size 1/10, because the contribution that we'll give would only be 2/10. It can never be negative. Because if it's negative, we're assigning a negative probability to an event. We will never assign a negative probability to an event. But you cannot interpret this the same way. When I say the P of X is 5, that does not mean the probability that I take on the value X is 5 in the continuous case. What's the probability I take on the value I take on the value X in the continuous case? It's 0. What does this mean to be 5? It means locally near this point X, my probability density function looks like 5. So if I look at what's the probability, I'm saying, between X minus epsilon and X plus epsilon, that's a band of width 2 epsilon. The probability density is about 5. If it's continuous, it's not going to change too much. It's going to be about 5 times 2 epsilon. So it gives you a way of approximating what's the probability you have an event very close to that value. Okay. So the next thing related to this is we have the probability density functions. What I want to look at now is the cumulative distribution functions. So cumulative distribution functions, abbreviated CDF. So the CDF of X is the probability at most X. So for instance, the probability that big X is less than or equal to little x. Think of it as the running sum, the running total. It's all, if here is x, it's the probability up to here. So in the discrete case, it would be the sum over all xk less than or equal to x of p of x xk. In the continuous case, it would be the integral from minus infinity to x of px of t dt. Why am I writing it as t dt? I need a different variable because I've got x here. So I have to use a different dummy variable for integration. So the cumulative distribution is just the probability you take on a value this high or higher. I'm sorry, this high or lower. Do we have to be careful about less than versus less than or equal to? Depends which case. In the continuous case, does it matter? No. In the continuous case, it doesn't matter because the difference in the continuous case is just x equals little x. In the continuous case, what's the probability of a singleton? It's 0. In the discrete case, does it matter? Enormously. In the discrete case, all of our outcomes are from a discrete collection. And if I don't have that equal sign, I could actually miss one of my events. This gives you another reason why we prefer working in the continuous case than in the discrete case. The discrete case can be a real pain because you can have these jump discontinuities. And all of a sudden, I move up and I hit a value. So if I'm looking at my cumulative distribution function for the dice, for tossing the fair coin, what's the probability? So we'll do the 3 tosses. So example, 3 tosses, a fair coin. So here's 0. The probability, the CDF is 0 up to 0. So we're going to plot the CDF. Plot of CDF. Where do I get my first jump? At 1. And at 1, it was going to be 3 choose 1 times 1/2 to the 8th. It's nice. Everything's always divided by 8. So the probability then jumps up to 3/8. And so the open circle means I don't take on the value here. The closed circle means I take on the value here. The next jump is at 2. And it's going to jump to 6/8. The next jump will be at 3, when it'll move up to 7/8. All right, did I do it right?
Aren't you,
Wait a minute.
0 be 1/8.
0 should be 1/8. Right. So these should all be 1/8 over here. All right. So this would be 4/8. This would be 7/8. This is 1/8 over here. And then over here, I would jump up to 1 at 3. And then from this point onward, my cumulative distribution function would always be 1. So if I look at the cumulative, yes?
Is there a jump at 0 then from?
Yes, you're right, yes. Thank you. Right. And then, so here's the 1/8 at 0, and it's open down here. Good. All right, so let's try this again. What is the probability you toss 3 die and your sum is -5 or smaller? 0. You're not going to have -5 heads. What's the probability you toss 3 coins and have -2 heads or smaller? 0. But now what's the probability you toss 3 coins and have no heads or smaller? Now it jumps up to 1/8 because you could have tail, tail, tail. Now we keep tossing and now we get to having 1 head. That will happen 3/8 of the time. So what's the probability we have at most 1 head? Well, we either had 1 head, which happens 3/8 of the time, or no head, which happens 1/8 of the time, and that gives us 4/8. If you want to know what's the probability we have 2 or fewer heads, it'll be 3/8 plus 3/8 plus 1/8. That'll be the 7/8. And you see there's a discontinuity. There are 2 very nice properties you can see. As we go off to infinity, what does the probability go to? 1. As we go down to -infinity, what does the probability go to? 0, which makes sense. And so what we want to do, I was doing so well in this swivel, what we want to do is we want to look at the most general kinds of cumulative distribution functions we can have. And we want notation. So what we're using right now, things like the probability big X is less than or equal to little x. This is not particularly suggestive notation. When you did calculus, you hopefully had good notation at some point, right? What was the big notation you used for integration? So what kind of notation did you use when you were integrating? If I gave you a function f, how did you represent the antiderivative? Capital F. And the advantage of that is you can quickly look down and you can see, the relationship between these two. So if we have little fx is the density of the random variable x, we can use big F of x, so this would be the PDF. We can use big F of x as the cumulative distribution function of x. And so what we would have here is big Fx of x is the probability that big X is less than or equal to x. It's the integral from -infinity to x of fx of t dt. And again, the first few times you're doing this, it's nice to have a little bit, overly assertive notation. Just really in your face, this is what I'm doing. I like to write probability big X is less than or equal to x. That makes sense to me. I understand what this means. And then I can represent this as my big function. Well, when you see a function like this, you want to differentiate it. And so if I take the derivative of big F prime, I want to now take the derivative of this. That's the fundamental theme of calculus. If I integrate from -infinity to x, then the derivative of the integral is the integrand at x. And I get fx at little x. And we also know that the limit as x goes to infinity of big F of x equals 1, and the limit as x goes to -infinity of big F of x of x equals 0. So these are extremely useful properties of cumulative distribution functions. One of your homework problems that is due technically on Monday, but Monday is reading period, so you may hand it in on Wednesday without any penalty, involves using the cumulative distribution functions. It is an amazing problem. It says if you can generate a random variable uniformly, you can actually use this to construct a whole slew of other random variables with other distributions. You only need to build one kind of random number generator. I will try to emphasize why this is so important. But how many of you remember your log laws? This is always dangerous to ask. So this is related to the most forgotten of the log laws. Anybody know the most forgotten of the log laws? To some extent, this is not surprising, as it's so forgotten.
I'm trying to think of a good, like,
What is the change of base? The change of base, remember to email me, the change of base formula for logarithms says if you can calculate logarithms in one base, you have them in all. In some sense, that's what this is going to allow us to do. If we can generate uniform random variables, we can pass from this to other things. Now, we can't generate uniform random variables, but we can pretend we can. And we can approximate that, and we can almost do that. Okay. So these are some very nice general properties of cumulative distribution functions. All right, what I want to do now is I want to, I think, finish today with a specific example. I'm not quite sure why it's no longer tracking. What I want to do is I want to finish with a specific example of a potential random variable, a potential continuous random variable. And I want you to tell me what you think. So consider f of x equals 2, I just want to make sure it gets to plus 3x minus 5x squared if 0 less than equal to x less than equal to 1 and 0 otherwise. Do you think that this is a probability distribution function? First of all, easy, continuous or discrete? Okay, so if anything, it's going to be continuous. What's the first condition to check? Yeah, I would check first, is it positive or negative? That's an easier condition to do than integration. So note, when you see something like this, what do you want to do? You want to factor it. And so if we try to factor it, I think I get 1 minus, yes, 1 minus x, 2 plus x. Is it 5x or, yeah, 2 plus 5x. And we can check, we get a negative 5x squared, we get a plus 2, a minus 2x, a plus 5x is a plus 3x. All right, writing it like this, it's not so bad to see that it's non-negative for the range we're looking at. So in the range we're looking at, x is between 0 and 1, so this factor is non-negative, this factor is clearly non-negative. This will be greater than or equal to 0 for 0 less than or equal to x less than or equal to 1. All right, satisfies 50% of the conditions we need. Now we want to integrate it. Which would you rather integrate? This nice, beautiful factored or this long polynomial? The long polynomial, excellent, good. So you are not misled by the phrasing. Why would you rather integrate this nice long polynomial? Yeah, power rule. We can integrate polynomial terms very easily. To integrate a product like this is a nightmare. So we want to integrate from 0 to 1 of f of x dx. And this is the integral from 0 to 1 of 2 plus 3x minus 5x squared dx. It's about time we finally use the calculus prerequisites for this class. So we integrate this, we get 2x at 0 and 1 plus, I think, 3/2 x squared at 0 and 1 minus 5/3 x cubed at 0 and 1. Well, everything at 0 cancels, so we get 2 plus 3/2 minus 5/3. All right, so if we combine everything, it's over 6. So that's 12 plus, I think, 9 minus 10. Is that right? So we get 11/6. Probability distribution or not? It's not a probability distribution. Fortunately, it is damn close to being a probability distribution. Of the two properties to fail, the one, if you have to choose one to fail, choose integrating to 1. This is very easy to fix. So how can we fix this and make this a probability distribution?
Multiply factors, 6/11.
Yeah, multiply by 6/11. And so as long as we multiply by 6/11, now we will get something that works. And so if anybody can figure out why this stops tracking at certain times, that would be extremely helpful. All right, so now we have our expression here. It almost is a probability distribution. So consider f of x divided by the integral from 0 to 1 of f of t dt. That new expression will integrate to 1. So we're basically just dividing by the value. So this now renormalizes, integrates to 1. All right, so this is terrific. So in general, this is going to be an exceptionally powerful observation when we start looking at processes. We will often be able to detect the x dependence up to a normalization constant. And you can try to calculate the normalization constant by brute force, and it will be painful. Or you can say, well, I know it has to integrate to 1. I can actually evaluate this integral very easily. Therefore, the normalization constant might be the following. We will see incredible applications of this. As an aside, who knows the area of a circle? Pi r squared. Volume of a sphere. Volume of a 4-dimensional hypersphere. Thank you. So how many of you remember your change of variable, your spherical change of variable from Calc 3? I'll let the record show there were no hands up. Not one person. How many of you remember, the answer is almost surely going to be no. If you don't remember the change of variables for spherical, how many of you remember the change of variables for n-dimensional spherical coordinates?
Oh, that one.
Yeah, then just set n equals to 3. Okay. So the whole point of this is you don't want to have to remember formulas like that. In a lot of problems, you will have things that only depend on the radial separation. Can somebody give me a physical process that only depends on the radial separation? Gravity, another one.
Electrostatic.
Yeah, electrostatics. You got to be fair, and if you're going to say gravity, they're really the same, except one has negative charges and positive. So these are forces that only depend on the distance between. They don't depend on angular configurations in space. There will be a lot of things like that. When you have spherical coordinates, you have all these angular things you don't care about. You frequently want to integrate out all of those things. This stupid-looking observation will allow you to bypass all those painful n-dimensional spherical coordinates. So right now I'm trying to just give you a little bit of a preamble as to why we care about stuff like this. It allows us to bypass some very messy things. To continue the, this feels like Family Feud, we asked, 100 Calc 3 students what their most hated quantities or subjects were in Calc 3. Top 4 answers are on the board. Show me change of variable formula. How many of you did the change of variable formula? With the Jacobians and all that stuff? This is often another one of those, painful topics, which, students do not enjoy so much the first time. It's extremely important, and when we're doing probability, to allow us to pass from one system to another. This allows us to bypass a lot of those things and just integrate out a huge number of variables and reduce it to a one-dimensional problem, which we can then integrate trivially. So there's a lot we've done today. A lot of it is just setting the stage for what comes later, but I want you to be a little bit motivated as you're reading the chapters. This is going to allow us to bypass a lot of the prerequisites for the course. All right, have a good rest of the day.